In this lecture, we are going to discuss about the transient response of source-free or undriven series RL circuit. So let us consider a series RL circuit as shown in figure 1. So here we have two different positions, position A and position B, and K is the switch. R and L are connected in series. VR of T is the voltage drop across the resistor, VL of T is the voltage drop across the inductor, and I of T is the current flowing through the circuit. So if the switch is kept in position A, then the voltage source will be connected across this series RL circuit, and if the switch is moved to position B, the source will be removed. Okay, so such a circuit is called as a undriven series RL circuit, okay, or source free circuit whenever the source is removed. So whenever the source is removed, the current flowing through the circuit will start decaying. Okay, so this is also called as a decay transient. So now we are going to consider that initially the switch K is kept in position A for a longer interval of time before transition. That is, before moving the switch to position D, switch was kept at position A for a longer interval of time. Okay, so this indicates that the network before transition is in steady state. So when the switch was kept in position A for a longer interval of time, current will start flowing through the circuit, and the current would have attained the steady state condition. Okay, so under steady state condition, the current will remain constant. Okay. So let us assume that at t is equal to 0, the switch is moved to position B. Okay, so before moving the switch, it is assumed that the switch was kept in position A and the circuit has attained the steady state. So the analysis of the RL series circuit is nothing but to find out the expression for the current decay in RL circuit. So before that, we have to find out the initial conditions. So let us calculate the initial condition of the current through the inductor. Okay. So now we have to draw the equivalent circuit for the position A. Okay. So already we have discussed the switch was kept in position A before transition, and the circuit has attained the steady state condition. Okay, so the current through the circuit is represented as I of 0 minus. So 0 minus represents the instant just before moving the switch to position B. Okay, here the inductor will act as a short circuit because the voltage drop across the inductor is given by L into di of t by dt. Under steady state condition, current will remain constant. So differentiating the current value will give you 0. So whenever the voltage is 0, then this will act as a short circuit. So under steady state condition, inductor will act as a short circuit. So I of 0 minus will be given by V divided by R. So this is the value of current at the instant t is equal to 0 minus. 0 minus is the instant just before moving the switch to position B. Okay. So immediately after closing the switch, that is at I of 0. And immediately after closing the switch, I of 0 plus. So under all these three conditions, I naught will remain the same because the inductor will not allow the sudden change in the value of current. Okay, so this is the instant at which the switch is brought to position B. This is just before moving the switch to position B, and this is just after. Okay, so under all these conditions, the current will remain the same. This is the initial value of current. I naught is equal to V by R. So let this be equation number 1. So this already we have discussed. L acts as a short circuit under steady state condition. So now for t greater than or equal to 0 plus, switch is moved to position B. So now let us draw the equivalent circuit as shown in the figure. And such a circuit is called as a source free or undriven circuit. So here in position B, the source is removed. So RL series circuit is short circuited. So the current will start decaying. Okay. So now we can apply KVL equation, that is Kirchhoff's voltage law equation, to this circuit. So let us assume I of t as the current flowing in the clockwise direction. So Kirchhoff's voltage law is given by sum of the voltage rise is equal to sum of the voltage drops in the closed circuit. So here we have no voltage source, so voltage rise will be 0, and voltage drops are the sum of the voltage drops across the resistor and inductor. So this is it. This is the required Kirchhoff's voltage law equation for the figure 3. Okay, let this be equation number 2. So now our aim is to find out the value of I of t. So we can rearrange this equation. So this can be written as r into I of t is equal to minus L into di of t by dt. Okay, or I of t is equal to minus L by r into di of t by dt. Okay, so this is equation number 3. So next we'll rearrange this equation. So we will bring this term downwards here and take this term towards the right left hand side. Okay, so we can write it as di of t by I of t is equal to minus r by L into dt. So now integrating this term on both sides, we can write ln I of t. So here this is in the form dx by x. So integral of dx by x is ln x. So similarly here integral of dt is t. Okay, so minus r by L into t plus k dash. So k dash is a constant. Okay. So now we have to find out k dash by using initial conditions. So already we have found out the initial value of current I naught. So now we can substitute in equation number 4. So ln I of 0 is equal to minus r by L into 0 plus k dash. So initial condition is nothing but t is equal to 0. So we are replacing t by 0 here. Okay, this was minus r by L into t. So t is replaced with 0. So this was ln I of t. So I of 0 plus k dash. So this term will become 0. So k dash can be written as ln into I naught. So I of 0 already we have derived in equation number 1 as I naught. Okay, I naught is given by V by R. So this is k dash value. So now we can substitute k dash in equation number 4. So we'll get ln I of t is equal to minus R by L into t plus ln I naught. So ln I naught is k dash. Okay. So again we can write this equation as ln I of t minus ln I naught is equal to minus R by L into t. Okay. So this is of the form ln A minus ln B. So ln A minus ln B can be written as ln A by B. So this term can be written as ln of I of t divided by I naught. Okay, that is equal to right hand side we have minus R by L into t as such. Okay, so now taking anti-log on both sides. So this ln will get cancelled and this term will come in the power of e. Okay, so I of t by I naught is equal to e power minus R by L into t. So now I of t is equal to I naught into e power minus R by L into t, that is equal to V by R e power minus R by L into t. So this is a required equation. So from the equation it is understood that for a source free or a undriven series RL circuit, the current is exponentially decaying. Okay, if we vary the value of t, the I of t value starts decreasing. Okay, so let us draw the graph like this. So let us consider the equation number 6. So if we substitute t is equal to 0 here, so this will become e power minus 0. E power minus 0 will be 1. So initial value of current is V by R. Okay, so initially when t is 0, current will be V by R. Okay, so after that if we start increasing the t value, the current will start decreasing. Okay, at one particular point called P, if we substitute t is equal to L by R. So t is equal to L by R is defined as a time constant. So if we substitute L by R, so this R by L and L by R will get cancelled. We'll get V by R into e power minus 1. So e power minus 1 is 0.368 into V by R. Okay, so this is defined as a time constant for RL decay transient. So after that, if we keep on increasing the value of t, the current will start decreasing. So when t is equal to infinity, here if we substitute infinity, e power minus infinity will be 0. So I of t will become 0. So the current will start from V by R and it will start decreasing and attains 0. So hence it is called as exponentially decaying. Okay, this is a exponentially decaying nature in the case of a source-free or undriven series RL circuit. So at point P, already we have discussed. So the current value is 0.36 times its maximum value. It is defined as a time constant. Tau is equal to 0.368 seconds. So now we can derive the voltage across the inductor. Voltage across the inductor is given by L into di of t by dt, that is equal to L into d by dt of v by r into e power minus r by L into t. So here v by r is a constant term. So differentiating e power minus r by L into t, will get e power minus r by L into t into minus r by L. So now this L will get cancelled. So the remaining terms are v into e power minus r by L into t. So we have minus here. So we have to add minus here. So VL is equal to minus v e power minus r by L into